Hello students, welcome to this lecture on the topic of power, and in this particular lecture we will look at more in-depth analysis on the switching probability and arrive at the switching activity factor, which will be useful in estimating the overall power of the larger digital circuit. Right, so what we will do is first try to understand the activity factor and then try to establish a kind of a relationship between the activity factor and then the logical gate. If I have a logical gate, then what should be the activity factor of that particular logical gate, and then apply that particular activity factor to estimate the one set of example consisting of the digital logic gates. And then we will also try to estimate the power, the switching power or the dynamic power estimation using two different kinds of an architecture. All right. So to start with, so this is an empty slide. What it means is I have to draw something. So what I've stated in this particular slide is a switching activity factor. So let me try to summarize what we have learned so far. So let me use the pointer. So the energy which we had estimated was alpha C VDD square, right? Where C is nothing but what is the total capacitance that is seen at that particular output node. And here, if we can take a simple example of an inverter and the inputs are connected, and then this particular output is this one. And the capacitance C is nothing but this particular capacitance. This could be the C load capacitance, right? So based on the input, I'll get the output to be switched. And then this energy is nothing but coming from the VDD rail, right? So the energy delivered by the VDD rail is nothing but the energy, so this for the capacitor to get charged, that means that the output to be doing the transition from 0 to 1. Now this particular alpha value is actually coming from how many, what is the frequency of the output node getting switched from 0 to 1, right? So this alpha is actually relating this output node switching frequency with that of the clock frequency, right? So let me draw a simple example. So if I have a clock frequency of let's say 1 gigahertz, so I'm going to draw 10 cycles. So 1 gigahertz means each time period will be nothing but 1 nanoseconds. So this will be my clock 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let me say that this is my clock. This is my clock signal. And let's say that based on the input here, the output is going to switch, and the output is going to switch 1 in 10 cycles. Right? I'm just throwing an example here. So 1 in 10 cycles, that means that, the output of this particular inverter circuit, so I'm going to write it as an output. And this is going to, have 0 most of the time. So only at the 10th cycle, 1 in 10 cycle, I will have an output going high, right? And then so on. So if I actually draw this, continue this in the 20th cycle, in between 10 to 20th cycle, I will have this, the output going high again. So this is basically the output, the output of the gate, or in this particular case, it's an inverter output, which is going from 0 to 1, or which is doing the transition from 0 to 1. And if I actually can relate this particular output frequency with respect to the clock frequency, right? So if I say that this is my output frequency, or you can also call it as nothing but the switching frequency from 0 to 1. So the number of transition is just from 0 to 1, so that the capacitor has to be charged. That is when the VDD will deliver the energy of the C multiplied by VDD square. If this frequency can be related in terms of alpha with respect to the clock frequency, right? So in this particular case, I have the clock frequency set to 1 gigahertz, and then the output is doing the frequency in every 10 clock cycles. So that means that the output frequency should be somewhere around 1 by 10th of the clock frequency. So I'll write it as 100 megahertz. The clock frequency is set to 1 gigahertz, let's say. So my alpha in this particular case will be nothing but 0.1, right? So in that particular case, if I have an alpha characterized or calibrated, for or characterized for this particular circuit in my chip, where the output node is doing the transition from 0 to 1 for every every 10 clock cycles. It is doing the transition of 0 to 1 once, right? So in every 20 clock cycles, I will have the transition from 0 to 1 2 times, and then so on, right? So I can have my alpha related like this. The overall energy, so this particular energy term here, right? This is nothing but the energy delivered by the VDD. I'm writing it as alpha C VDD square. And what it says is, it is nothing but the average energy that is being delivered, right? That is being delivered, the energy delivered for one transition at the output node from doing the transition from 0 to 1 will be nothing but C VDD square. So this alpha for this particular circuit, which is calibrated to have a value of 0.1, what it implies is, if I consider one clock cycle, the energy, the average energy that is being delivered by VDD is 0.1 C VDD square. The energy delivered in the second clock cycle is 0.1 C VDD square. The energy delivered in the 8th clock cycle, it is 0.1 C VDD square. 9th clock cycle, it is 0.1 C VDD square. 10th clock cycle, it is 0.1 C VDD square. So from the clock cycle of 1 to 10, the overall energy that is being delivered by the VDD turns out to be 0.1 multiplied by 10 C VDD square, which is nothing but C VDD square. Right, so what it does is, this particular energy term is nothing but the average energy delivered by the VDD for one clock cycle. Right, and that is where this alpha is coming. Right, so in this sense, alpha is nothing but, it shows an average energy that is being delivered, right, by the VDD. Alpha is also used to find out the power delivered by the VDD, right, is nothing but C VDD square, and then alpha here, and then I'll write the clock, right? It is nothing but the C VDD square multiplied by the F switching or the F output, right? Instead of F switching, I can write it as F into alpha clock. All right, so this will give me the instantaneous power that is being delivered by the VDD, or rather it can give me the average instantaneous power that is being delivered by the VDD, right? So across this particular clock cycles, at any point of time, right, I will get an average value of the power as nothing but alpha C VDD square into F clock. All right. So in this particular case, alpha is equal to 0.1, and so that means that the output node is switching actually 10% of the clock frequency. Right, and we actually want alpha to be lower and lower, so that if it is lower and lower, the overall energy, right, that is being delivered by the VDD will be less, and the overall energy that is consumed by the circuit or delivered by the VDD rail in our design will be actually be less. Right, so let's take an example here. So I'm saying that let's try to find out a power or whatever energy. So I can say that if I can find out the average energy that is delivered by the VDD rail, and if I can get that, alpha C VDD square multiplied by F clock will give me the average power, right? So in this particular case, I've got this particular circuit, and let's see what is the logical output of this particular circuit given the inputs A, B, C, D. So here the X output will be A, B bar, Y will be C, D bar, and then the NOR of it, so I'll write it as Z is nothing but A, B bar plus CD bar, and then the whole bar, right? So it turns out to be nothing but AB bar. So if I apply the De Morgan's theorem, so this particular entity and this particular entity, I can write it as CD bar. So it is nothing but AB CD. So this is the logical expression for this particular circuit. Now, if I want to actually find out the overall average energy of the overall circuit, then I actually need to probe the energy here, I need to probe the energy here, I need to probe the energy here, right? Assuming I will have the parasitic capacitance. So here I need to find out what is the capacitance, the total capacitance here, the total capacitance here, which we can find it out if I know the input capacitance, if I know the parasitic capacitance based on the width of this particular gates. Right, and then similarly here I should be able to find out the overall capacitance here based on the width of this particular gate, And assuming that this is not loaded, we don't have any kind of a load connected to this particular output. And if it is floating, we'll have only the parasitic capacitance of this particular gate. So knowing C1, C2 and C3, I should be able to find out what is, the capacitances is known, but I need to also find out what is alpha 1, alpha 2 and alpha 3 here, right? So for finding out the activity factor, it requires the probing at every output of the gate and multiply the number of transitions from 0 to 1 by the C VDD square, right? So if I have to do C1 VDD square, I need to multiply by alpha 1, and alpha 1 I can only find it out if I know the Fx switching frequency of the X output node, switching frequency of the Y output node, switching frequency of the Z output node, and then related to that of the clock frequency. And then I should be able to find out alpha 1, alpha 2 and alpha 3 here, and then put it across that particular equivalent capacitance and then find out the overall energy at each of this node, right? But this is a very tedious process. Now, what is a tedious process? The number of transitions at individual nodes, finding the number of transitions at individual nodes is a very tedious process. Hence, an alternate probabilistic based method is used. All right. So if I have a larger circuit, it's only 3 gates here. So if I have millions of gates, if I have 10 raised to 6 or 10 raised to 9 such gates, or the transistors forming the gates, then I need to probe at each and every point, and probing at each and every point of the gates, and then evaluating the switching, the transitions or the switching or the activity factor at each of the output nodes, right, becomes a very tedious process. And to avoid that, what we'll do is go to the probabilistic method. Let's see what is that probabilistic method. So the probabilistic method says that all the logic gates have a logic functionality, right? So whether it's a NAND gate or a NOR gate or whatever other gates, combinatorial circuits, there is a logical expression. So we can actually write the output in terms of the input, right? And the activity factor at each of the outputs of this logic gates can be defined as nothing but the conditional probability, right? Conditional probability, where it includes 2 probabilities. One is the probability of it being, of the output of the gate being 1. The other probability is that the probability that the output node I is equal to 0. And what it says is, it is nothing but the conditional probability of Pi and Pi bar, the probability that the node I, for a gate I, so let's say that I have an gate here, there are millions of gates, and if I pick one of these gates, I'll say that this is the gate I, whatever is the number of inputs here, and here this will be the output. There could be multiple outputs. I'll pick one of the outputs, and this particular output node, right, is doing the transition from 0 to 1, right? So what it means is I need that particular output node being at 0 in the previous clock cycle and being at 1 in the next clock cycle. So in one clock cycle, in the previous clock cycle, it should be 0, and in the next clock cycle, it is 1. So that's why it is Pi, the probability of that particular gate output or the node to be at 1, and Pi bar is nothing but the probability that the gate output node is at 0. Right? So it is written as 1 minus Pi and then multiplied by Pi. Right? So this is by definition the activity factor, and it's a very theoretical approach which helps us to do a rough calculation of the overall power estimation or the energy estimation of the overall higher order digital circuit, right? Moving ahead, now what is this probability? What is this Pi? How do I calculate Pi? And then if I calculate Pi, I should be able to find out what is Pi bar, right? So let's take up a 2-input NAND gate. So I have 2 inputs to the NAND gate, and the output is Y. So for a 2-input NAND gates, there is, I can form the truth table. If it is 0, 0, I'll have 1. If it is 0, 1, I will have 1. If it is 1, 0, I will have 1. If it is 1, 1, 1, I will have zeros. So in this case, if I take this particular, last input combination, 1, 1, giving an output of 0, I can write my probability for this particular logic gate, which is a 2-input NAND gate, as 1 minus PA and PB. So this is 0. So that's why it is 1 minus, and then what is the input probability? It is being 1, so that's why PA, PB. Alright, so the output of this NAND gate, given the input probability of A and B, I should be able to find out what is the output probability of this, the output node being at 1, right? Based on the input, input probability being at 1, I should be able to find out the output probability. This is the output of the 2-input NAND gate being at 1. So the probability, the output of the 2-input NAND gate being at 1, I should be able to evaluate based on the inputs being at, the probability of the inputs being at 1. So it will be Py is equal to 1 minus PA, PB. And let's take a look at the 2-input NOR gate. So for the 2-input NOR gate, based on the input combinations, again we will have 4 combinations. All of them are 0 except the first combination, which is where is the input are 0 and 0. I'll get a 1. So this, the output node Y being at 1 is nothing but PA bar and PB bar, right? PA will give me the output being the input of this particular 2-input NOR gate being at 1, and PB will give me the input, the other input being at 1, but we need 0 and 0, that's why it is the complement of that, so PA bar, PB bar. So now I have the output probability of the 2-input NAND gate and the output probability of the 2-input NOR gate given the input probabilities. Input probabilities means PA, PB is given, PA, PB bar is given, then I should be able to find out the output node probability. Right, especially for the 2-input NAND gate and 2-input NOR gate. Let's take a look at the other standard gates. In this case, 2-input AND gate and 2-input OR gate I have given, or I have mentioned here. So based on the A and B, I'll get a Y output for the 2-input AND gate, and PY is nothing but stated as PA and PB. PA multiplied by PB. That will be the output of the 2-input AND gate being at 1 is nothing but PA and PB. And similarly for the 2-input OR gate, it will be nothing but PY will be nothing but 1 minus PA bar, PB bar. So in our next example, we'll try to use these 2 probability nodes to find out the probability at the output node, right? So the output node being at 1, I should be able to find out, right? If I have a 2-input NAND gate and if I have a 2-input NOR gate, so the output of the 2-input NOR gate being at 1, we should be able to evaluate using this particular expressions. Right, so one is 1 minus PA, PB, another one is PA bar, PB bar. And use this to find out what is the activity factor. So if I want to find out the activity factor of the 2-input NAND gate, right, I should be able to use this and then find out saying that alpha activity factor is nothing but PY and PY bar. For a 2-input OR gate, I should be able to find out the same thing, PY bar. Right, so this is what we had seen in the last slide. So hope this is clear at this point of time. Moving ahead, let's take an example of this multi-stage architecture designed for the logic Y is equal to ABCD. So this is what we wanted. This is what where we are started from. So we had a 2-input NAND gate in the single stage, and then followed the output of that is going to the next stage of the 2-input NOR gate. So that the Z output is nothing but ABCD. Right? Let's say that the input probabilities are characterized and given to us saying that PA, PB, PC, PD is equal to 0.5. So what it really means is the probability of these inputs, whatever the 4 inputs are there, that being at 1 is 50%. So that being at 0 is also 50%. So we are giving a kind of an equal distribution of for the logic 0 as well as logic 1 input. So if I consider that, I should be able to evaluate the probability at the X node, at the Y node, at the Z node, right? And then find out what is the activity factor at X, Y, and Z, and then find out what is the overall energy delivered by the VDD for 1 clock cycle. So I'll say that it's an average energy that is being delivered by the VDD, right? Once I have the energy, I should be able to multiply that with that of the clock frequency and then find out the overall power, right? Or whatever, the average power, also called as a dynamic power. Right, hope this is clear at this particular point of time. So let's go ahead, let's proceed and then try to evaluate the probabilities at this particular nodes X, Y, and Z. Right, so Px, it's the probability at the output of the 2-input NAND gate is nothing but 1 minus PA and PB. So PA and PB are 0.5, so it will be nothing but 0.25 here. Multiplication of PA and PB, 1 minus 0.25 will be 0.75. Alpha x will be nothing but px bar multiplied by px, so it will be 0.1875. Py will also be the same because C and D also have the similar probability. So I'll have 1 minus PCPD, that is 0.75. Activity factor of Y is 0.1875. The PZ is nothing but the two input NOR gate, and we know that Px bar, Py bar. Here the Px bar, Px is 0.75, so Px bar will be 0.25. Py bar is also 0.75, so Py is 0.75, so Py bar will be nothing but 0.25. So Pz will be nothing but the probability of the output of this two input NOR gate being at 1 will be nothing but 0.25 the whole square, 0.0625. So now I have evaluated the probability at all the three output nodes. And if I want to find out the activity factor at each of these three output nodes, I will do it. Alpha x is nothing but px bar. Px will be 0.1875, 0.1875 here, alpha y. And alpha z will be nothing but pz bar into pz. Pz bar is nothing but 1 minus 0.0625, and then pz is 0.0625. So if I do that multiplication, I'll get 0.05859, which is nothing but 15 by 256. Right, so 0.05859, that will be my alpha z. 0.1875 is my alpha x, and alpha y is 0.1875. Right, so I have three capacitances here, and I have got the three activity factors. Moving ahead, so the total power, which will be nothing but if there is a power term, I'll just multiply the energy term with that of the F clock. Right. So, so the total power will be nothing but alphas multiplied by the individual capacitances, right? And then I have three output nodes, so I will have the three such alpha multiplied by the individual node capacitances multiplied by F clock into VDD square. VDD, if I can consider this to be a 65 nanometer technology node, so I can have it as 1 volts, right, as a real voltage. So now I should be able to find out easily what is, alpha x is 0.1875. And alpha y is also 0.1875. Alpha z is 0.05859. Right, so let me reconfirm that, 0.05859. So this will be my alphas, and then the multiplied by the respective node capacitances, and then multiplied by the F clock and VDD square will give me the total power.